everybody. Welcome to an exciting introduction to computer architecture. I wanted to give you a brief rundown of some of the basics. Normally we interact with a computer using an application, and that goes through some operating system and then down to the hardware. But underlying this hardware there is a basic architecture, and this is where I'd like to focus some of our considerations for today. So when we think about what computers are made of, normally we do our switching with transistors, at least in modern electronic general-purpose digital computers. And the transistor dates back to 1951 when Shockley and Breton basically created a point contact amplifier out of semiconductors. This essentially led to one of the inventions that revolutionized electronics for amplification and switching, obsoleting most of the usage of tubes, or what are sometimes called valves, depending upon which country you're from. For the digital applications, transistors have been imaged into silicon through a mask that is then integrated into a single chip known as an integrated circuit. The integrated circuit fabrication has given rise to a very large semiconductor industry. When we think about transistors, we think about typical fabrication materials. It could be gallium arsenide, but typically we use silicon. And the silicon is often created in an extraordinarily pure form known as a silicon ingot. And this is then sliced using a wafer slicing machine into something that can be imaged with multiple chips onto a single dinner plate sized wafer. The wafer is then sliced and diced and mounted onto a die that effectively allows us to wire contacts to an external point, typically a pin or a ball in a grid array, and these are then used to make our connections. Photolithography. Lithography means stone writing, and photolithography means essentially imaging through what must be a mask onto the silicon. The important dimension, the critical dimension, is typically used to determine the smallest feature that can be resolved using this photolithography technique, and it is linear in the wavelength and inversely proportional to the numerical aperture of the optical system. Typically, we have seen 193 nanometer imaging being used, but we have since transitioned to a soft X-ray system based in 13 nanometers, known as the ASML twin scan machine. This is a machine which has been priced fairly high. Intel keeps about $250 million of cash as a strategic asset used to continuously update what is essentially 1 million square feet worth of clean room space, and this is used in order to be able to fabricate chips in mass quantities. The transistor functionality is such that it can be used to amplify, or it can be used to switch signals. Typically, when we're dealing with computers, we're more concerned with having it used in saturation, which is to say, used as a switch. But it is the case that as engineers, we're also interested in using the transistor as an amplifier. And in fact, the transistor can act in funny nonlinear ways, that is, as an amplifier, when it gets loaded down. So we use the transistor to create gates, and once we have the gates, we can essentially fabricate large systems. Here is an example of a transistor on the top. That is a dual inline package. And then there is a small discrete transistor in the lower left, and then we have a simple two-junction light-emitting diode on the lower right. This is the first processor chip, 1971, and it was used for building a calculator called the BusyCom calculator. This chip is essentially a computer on a chip, and this central processing unit had very limited capabilities, could only add and subtract, and only 4 bits at a time, the 4004. Then comes the larger computers, and here we can see an Athlon 64-bit processor. So when we use logic gates, we typically use them to be able to store a bit of memory. And normally when we are constructing our finite state machines, we can start with logic gates, or we start with something a little bit higher level, perhaps flip-flops. The von Neumann machine, which we often refer to, is actually an architecture, and that's where the memory is used to store not just the program, but also the data. And by storing both in the same memory, we are able to essentially alter the program with relative ease. This is a typical CPU board, and what you can see down in here are some DIMM slots. This is dual inline memory modules, and these are used to add some memory to the system. Over here we see a central processing unit socket, and there's also some what they call bus slots, and these bus slots have different shapes and sizes to accommodate different types of cards. So typically what we see inside of a central processing unit is a fetch, decode, and execute cycle. And in that cycle, we're able to find that if we execute just one instruction at a time, we can essentially be band limited by what's known as the CPU clock. And so the CPU clock will determine the overall program speed. These cycle times for the clock are not the only limit. You may also find that the number of clock cycles per instruction changes, and so that an increase in clock cycle frequency is not necessarily going to result in as much performance improvement as a change in the number of cycles per instruction. RAM, or random access memory, is typically used for the computer's main memory, and most modern machines typically address 1 byte at a time, and it's often possible to address many megabytes or gigabytes even of memory. This is an example of a RAM module, and you can see the different chips have been mounted onto the module, and then it was assembled to be able to plug in to a single SIM slot. The RAM comes in both static RAM and dynamic RAM. The dynamic RAM is volatile, and so is the static RAM. But the dynamic RAM is fabricated using a capacitor, which has a charge that declines as a function of time, whereas the static RAM will retain its memory for as long as power is applied and does not require the so-called refresh that a capacitor needs. But fabricating RAM with a capacitor enables you to create smaller, denser, and cheaper RAM. And so dynamic RAM is very typical when people are working with, let's say, normal performance RAM, and static RAM is typically used for higher performance RAM. Read-only memory will retain its state even after the power is lost. And so typically with read-only memory, you can only read from it, but somebody has to write to it prior to you reading from it. You can fabricate it with instructions at the factory, or you can find erasable read-only memory or electrically erasable read-only memory, and these elements are very typical in most computer systems. Registers are very special memory locations typically used on the CPU chip, and they are high performance, high speed, limited size memory locations that are used for casual storage and retrieval of variables at the assembler level or in the machine code level. The instruction register is one such example. What you typically do when you fetch an instruction is you store it into the instruction register. Then you can execute it using perhaps another register such as the accumulator. You can transfer data using memory data registers. You can latch the data using a memory address register. And then there's a program counter, another special register, which allows you to determine what the next instruction address will be. So here are two of the many registers in a computer, the instruction register and the accumulator, and these can be instantiated from locations in memory. Von Neumann-style machines typically have a machine language, and that is an instruction that it knows how to execute. For example, CIA, complement and increment the accumulator from the PDP-8, allows you to do 2's addition and subtraction because it gives you 2's complement. 7404 is a low-level octal machine instruction for doing no operation, also from the PDP-8. You can program these things directly in through the front panel of the PDP-8, which has the fancy blinky lights. Instructions typically consist of two numbers. One is the address of the memory unit to be accessed, and the other is an operation code of the instruction. So opcodes, you could have perhaps 128 different opcodes in a 7-bit area, and then you could have some memory address. And this gives you a full 32 bits, and you can use that to encode machine language instructions. So for a 32-bit machine, like for example Java Virtual Machine, you might only have 128 different opcodes if you were only going to use 7 bits per opcode. Information transfer inside the CPU is typically done in parallel. We want to be able to maximize the average throughput of data transfers, and so if you have a 64-bit machine, you'd like to be able to transfer 64 bits in parallel on a data bus that has 64 bits in it. If you have a memory bottleneck, that refers to the fact that you are I/O bound when you're doing your computations in your CPU. One way in which you can address the memory bottleneck and cease to be I/O bound is to have separately transferred data using a direct memory access, or DMA as it's sometimes called. And what that does is it reaches out to the memory and stores the data in a high-speed cache. And the cache may be high performance, but typically it's relatively small. The cache memory is stored inside of the CPU, and the CPU will have some sort of a DMA controller for moving memory from main memory to the cache. So the central processing unit's basic life cycle is it fetches the next instruction, decodes the instruction, executes the instruction, and then goes to get the next instruction. And that's all part of the so-called pipeline. And so this is known as an instruction cycle. You want to have a memory address register, MAR, a memory data register, MDR, and some control element which is going to be able to go and get memory from the main memory location where the RAM is stored across the data lines and into the memory data register. Inside of the CPU we have some very basic block diagrams. The memory address register, MAR, the memory data register, MDR, both communicate directly to the RAM. There's a CPU bus, and then there's a program counter, that's a register, that keeps track of which address you're on, an accumulator for doing operations, a arithmetic logic unit, and then a instruction register with some control. And then there's a clock governing the entire thing so it can be run synchronously. So now we can see the different registers: program counter, instruction register, arithmetic logic unit, and an accumulator or work register. The accumulator, they could call that the A register, but oftentimes it's the case that you can have many registers inside of the CPU. So here we are looking at the address of the next instruction transferred from the program counter to the memory address register, presented in a stable way to the RAM until the memory on the data bus is guaranteed to be valid, and at which point it is latched in the memory data register. So once we get the memory in the memory data register, we can go and transfer another memory address into the RAM and proceed to retrieve the memory data register. That goes into the instruction register, and then the instruction register has to do an execution and a decode, and we expect that there would be some result written back to memory. And the program counter has to be able to respond to that instruction. So if it says, jump to another address, the program counter gets loaded, and then the program begins executing at the new address. So the semiconductor industry has been in a race to the bottom for many years. And what it's been doing is it's been trying to make everything smaller, cheaper, and faster. And in doing this, we can see Moore's law being used. Here is a logarithmic scale of the transistor count as a function of time. And we see a rough doubling every 18 months or 2 years, depending on who you ask. This enables us to effectively get far more compute power for the given cost as a function of time. So that's a remarkable thing to behold. And in fact, some people have said this is the death of Moore's law. We can't keep increasing the critical dimension. But in fact, now that we're on to the new 13 millimeter illumination standard, the critical dimension has been reduced somewhat, perhaps by a factor of 10. And so Moore's law continues, at least so far. But there are problems. One of the problems is that we're running out of room at the bottom. We're going to get down to the size of atoms, and when that occurs, things are going to get rather tricky. Also, I think that there's this element of heat. Heat will effectively keep densities from increasing without bound unless we can find some way to manage the heat. So what can we do to change things? Well, we could think about quantum computing. I like to think that by the time quantum computers are common, I'll be retired. Or another way to put it is quantum computing is the future, and it always will be. Maybe quantum computers will happen. I don't know. In general, they're trying to do a computation based on the spin of an atomic particle. People say that this is being done, and I have to believe it. However, I must tell you that it's healthy to be skeptical about these new technologies. There are molecular computing paradigms, and there's also optical computing paradigms, all of which are promising, all of which are topics of current research, none of which have become particularly practical. And so that's what I have for you for this particular lecture. I hope you enjoyed it, and I thank you very much for your time.